Hello, my name is Luiz Giacomossi. I am a graduate student at the Instituto Tecnológico de Aeronáutica, and I'm going to present our paper entitled Cooperative and Decentralized Decision-Making for Low Wingman UAVs. The other authors of this paper are Professor Stiven Schwanz from the Eindhoven University of Technology, José Fernando Bracalion from SBR, and Professor Maximo from ITA. The overview of this presentation is, I'm going to introduce the context. Then I'm going to proceed to the main decision-making architectures found in literature. The scenario of interest, where we apply the low Wingman concept. The simulator that we developed for this paper. The decision-making development for a kamikaze UAV and for the low Wingman UAV. Then I'm going to proceed to the experiments carried on and the results. And I'm going to conclude and show ideas for future work. The term decision-making is the cognitive process resulting in the selection of actions among several possible alternatives. Modern decision-making enabled the so-called cooperative engagement capability among multiple networked agents that work as a team in a network, make decisions in group to engage and disable aerial threats. Those agents can be manned or unmanned aircraft systems, also known as manned-unmanned teaming. This idea includes the concept of a loyal wingman aircraft that works under the tactical command of a manned leader. This aircraft can be replaced by UAVs. With the combination of these UAVs with artificial intelligence, we can automate most of the decisions done by combat UAVs, achieving an autonomous UAV that can be used to allow the human pilots, to focus on the big tactical picture in modern warfare scenarios. Decision-making architectures. The most popular methods found in literature are the finite state machines and the behavior trees. Both methods are often designed by humans. This design is empirical and based on good practice. This process is iterative, with the agent performance being evaluated by experts in the area or through statistics. Optimization methods and machine learning techniques can be employed to optimize parameters or to learn new behaviors for these agents. The decision-making can be broken down into so-called behaviors, which are models tailored to solve subtasks in the context. State machine is the simplest and the most common technique found in decision-making. The agents only have a finite number of states. The states represent the behaviors for the agent. The machine guarantees the permanence in a certain state, unless there is a transition. The developer is responsible for defining the behaviors, or encoding the behaviors, and in the conditions that are triggered. These conditions can often be represented as parameters in the system. Behavior tree. The behavior tree has become the standard decision-making method in the AI games industry, as it solves many problems encountered with the FSMs. It changes the decision-making paradigm to a tree, where the behaviors are coded as nodes. There are two types of nodes, compose node and leaf node. The compose node controls the behavior tree logic, and the leaf node executes the behaviors or check conditions. Here you can see a condition and a behavior. The node returns a status. Success, failure, or running. For example, the sequence node will execute all the nodes on the left branch and then proceed to the right branch. If one child fails, he will return failure. In this table, you can see all the logic present in all the nodes. Scenario of interest. In our paper, we introduce a novel scenario based on the loyal Wingman application. This scenario has two teams, a mom team and a kamikaze swarm. The mom team is composed by loyal Wingman agents and a leading drone. This team must engage and disable these kamikaze drones that are trying to attack both the protected area and the leading drone. The simulation is considered over when the leading drone is destroyed, when the protected area is hit by 5 drones, or when all loyal wingmen were destroyed. The leading drone is controlled by a human. All loyal wingmen's agents are autonomous. The loyal wingmen have two kinds of guns, a freezing gun and a vaporizer gun. The freezing gun is a mid-range gun, and it slows down the threat. The short-range gun is the vaporizer gun that destroys the threats with a single hit. A simulator was developed for this study. It was developed using Python and the Pygame library. The UAV model is composed of a position controller, which controls the pose of the drones, and a collision avoidance model using the potential fields technique. The simulator is intended to evaluate the application of the loyal wingmen in the scenario proposed, where we focus on the evaluation of the decision-making techniques, abstracting realistic physics models. The simulator can be seen in figure 5. Here we can see a kamikaze swarm attacking both the protected area and a mom team. In figure 4, we can see the leading drone at the center and 10 loyal humans surrounding him in a protective formation. The decision making for a kamikaze is pretty simple, and it was developed using a state machine, with each kamikaze having an identical copy of this machine. There are 4 behaviors. The default is the wait state. In this state, the agent will wait for the definition of a target to attack. Once the kamikaze chooses a target, he will seek this target and remaining in this behavior until it is destroyed. The targets are chosen with equal probability, and they are the leader, or the protected area, or the loyal wingman, a specific one. In this state, the kamikaze will choose the closest loyal wingman to attack at every 1 second. In this figure, we have the behavior tree for a loyal wingman agent. The behaviors are 5. Chase threat, go to formation, attack using vaporizer, freeze threat, or sacrifice. The default behavior is go to formation, where the loyal wingman will remain in the formation to protect the leader. Once a threat is in engagement range, the behavior tree will execute the chase threat behavior. Here, the loyal wingman will leave the formation in order to pursue the threat. When the loyal wingman is in weapons range, the behavior tree will select one of the possible alternatives to attack the threat. It can be by using the vaporizer gun, the freezing gun, or by sacrifice. Usually, the loyal wingman will first slow down the threat by using the freezing gun, then he will get closer to the threat and use the vaporizer gun to neutralize it. Once there are no more ammunition in both guns, the loyal wingman can use the sacrifice by hitting the kamikaze with his own body frame as a lost result tool. The experiments carried out used 10 loyal wingmans and 4 kamikazes, constantly attacking. Once a kamikaze is destroyed, another one appears, maintaining a constant flow of attack. 2 experiments were performed, both for 500 iterations. In the first experiment, the behaviors on the loyal wingman's tree and its parameters were manually adjusted, so it was an experiment based on trial and error. After this initial adjustment, we used the particle swarm optimization, PSO, to tune 2 parameters, the distance engagement and distance formation. Distance engagement sets a threshold distance for a loyal wingman to leave the formation in order to pursue a threat. The distance formation is the radius of a formation, with the leader at the center. The metrics that we observed are the survival time until the game is over, the enemies destroyed by the loyal wingmans, the number of loyal wingmans that survived an iteration. And from these metrics, we defined this fitness function that was empirically defined, and we applied this function to be maximized by the PSO algorithm. First, assuming a reference to analyze the results, the fact that 10 loyal wingmen were used have only 100 ammunition for threat elimination. That is 10 for each loyal wingman in the vaporizer gun, and that this weapon has a 95% hit probability. At a perfect case, we would get 110 kills, with 100 kills by the vaporizer gun and 10 by sacrifice when out of ammo. That gives us a long-term average of 105 eliminations. The results of the experiments can be seen in this table. In the first experiment, the agents eliminated around 90% of the total threats. This result indicates us that the loyal wingman agents, using the developed behavior tree, even with parameters found empirically, were effective as an autonomous defensive system. In the second experiment, both parameters were optimized in order to obtain the highest defense effectiveness. The agents in total eliminated an average of 102 kamikazes. That's close to 90% of the total threats. This experiment also resulted in a better survival time, 27% longer, and resulting in 20% less loyal wingman survivors at the end of the iteration. This indicates us that the loyal wingmen were more effective when the parameters were optimized. Now I'm going to show a short demonstration video of our simulator running. In this paper, we have proposed a novel defense scenario with completely autonomous low-wing UAVs. The UAVs cooperate to engage and neutralize a swarm of kamikaze drones. Decision-making methods were employed to allow these applications to be autonomous. Both the intelligence for a low wingman and for a kamikaze have been developed. We have seen threat elimination of around 93% after optimization. We also developed a simulator for proper evaluation of these techniques. With simple engagement rules, we have seen the emergence of teamwork for threat neutralization, with loyal wingman agents developing a specialized defense behavior. For example, a loyal wingman exhibits a specialized behavior to defend the leader. Formation and defense specifications should be further evaluated. Consensus algorithms may also be investigated. Reinforcement learning may also be applied to have more complex behaviors. Tests with realistic physics for further evaluation shall be performed, since in this project we have focused more on the development of the decision making. I would like to thank Embraer for my scholarship, and I would like to thank you for your attention. These are the references. Thank you.